So today and tomorrow, we're going to split this one into two parts. We're going to talk about transformations of function graphs. So both days we're going to be looking at what are the ways you can transform the graph of a function y equals f of x. And we're going to be talking about the reasoning standard for mathematical practice. So really what we're going to look at this way is we're going to be really looking at numbers, or in this case graphs, in many different ways and different ways that we can represent them. So that helps us reason abstractly and quantitatively. So not only are we going to be kind of examining number patterns, but we're also going to put that in terms of an algebraic expression. All right, so we're only doing the explorers today. We're going to do them together. And then you'll do a little bit of homework based off of that, and then we'll do the explains tomorrow. So we're splitting this lesson into two. So we're going to investigate translations of functions. So translations is basically a fancy word for when you're going to slide your graph. So we're sliding our graph, okay? You can transform a graph of a function in many ways. You can translate a graph vertically or horizontally or vertically. That might not be bad to underline. Transform horizontally or vertically. You can stretch or compress, which is a transformation, not a translation. Stretch or compress the graph horizontally or vertically. And again, you should be underlining. You could do this with your regular pencil or colored pencil if you wanted it to stand out. You can reflect the graph across the x-axis. So we can reflect across the x-axis or the y-axis. How the graph of the given function is transformed is determined by the certain numbers we call parameters, which are introduced in the function. So parameters are numbers that are introduced in the function. The graph of f is shown. Use this graph for exploration. So this is what they're considering the graph of f of x. All right. So again, this is our f graph. They're saying that first graph g of x equals f of x plus k. So we're going to take the f graph and we're going to add some number k to it. K is the parameter. K is in general. We can change that value of k in order to translate the graph in different directions. So we're going to let k equal 4 so that that g of x equals f of x plus 4. Complete the input-output table, then graph g. In general, how is the graph of g of x equals f of x plus k related to the graph of f of x when k is a positive number? So we're going to come back and answer that question. Let's start by just taking our function and adding 4 to it. So what they did was they gave us our x value. They gave me the value of the actual f function at that x value. And then all we have to do here is add 4 to that number. So when we added 4 to negative 2, we get 2. When we add 4 to 2, we get 6. When we add 4 to negative 2, we get 2. When we add 4 to 2, we get 6. So now we're going to plot these x values with this column of y values. So I'm going to go negative 1, 2, 1, 6, 3, 2, and 5, 6. We're going to go ahead and connect those dots. Now let's go back and answer that question, okay? It asks, in general, how is the graph of g of x equal to f of k related to the graph of f when k is a positive number? Well, we did an example of a positive number, and you'll notice that it moved the graph or slid the graph or translated the graph is the best word. It translated it up. So let's see. Oh, we didn't leave there's a line on yours in your notes. So just go ahead and fill that question or that answer in on the line. So we would say that when k is positive, g of x equals f of x plus k is translated up k units. Because notice it went up 4 units, the same number that we put in. Okay. All right. Now try a negative value of k and g of x equals f of x plus k. Let k equal -3. Okay, so we're going to graph this function, which means we're supposed to be subtracting 3. And we're going to complete the input-output table and the graph on the same grid. So we're going to put this up on the other grid that we had. So let's see, we're subtracting 3, and we get -5. Subtract 3 again, we get -1. Subtract 3, we get -5. And subtract 3, we get -1. So we're going to plot these points and these points, and I'm going to go ahead and do that in a different color. Okay, so I'm going to go back and do that on the same graph. So we're going to go... It was -1. Let me look at my number again. -5 and -1. Okay, so -1, -5. 1, negative. It was -1. And then 3, -5. And 5, -1. So there's our graph translated. In this case, we translated it down, and it went down 3 units, which was the value of k. So let's answer this question now. In general, how is the graph of g of x equals f of x plus k related to the graph of f when k is a negative number? So, let's see. How did I phrase that before? When k is positive. So we're going to go when k is negative. Okay. G of x equals f of x plus k is translated down, it says down 3 units. I notice I don't put -3, I put the word down. Down is taking place of the negative sign. All right, now they have a slightly different, they didn't give us a table on this one, they gave us a slightly different method for putting in our values. Okay, now we're going to graph g of x equals f of x minus h. Notice this is different. Before, they had a k and it was outside that function. It was outside the parentheses of the function, and it had an up and down effect on the graph. Okay. So this is different. This h value is inside the parentheses, okay? So we're going to let h equal 2. And we're going to graph this, complete the mapping diagram, and then graph g of x. To complete the mapping diagram, you need to find the inputs for g that produce the inputs for f after you subtract 2. Work backwards from the inputs to the missing inputs by adding 2. Okay, so we'll do the in general. So basically, let's understand how this worked this way. So if my input for g, I subtract 2 from it to get my input from f. So 1 minus 2 equals -1. So my output for f would be -2.